the same direction.
Right, then thank you very much for being here. I also want to thank the organizers for giving me the opportunity to be here at this fantastic program. That's a lot of fun. I enjoy it a lot. And I'm also grateful that I can give these talks here. So let me maybe first tell you what I'm going to do. So I'm giving 3 talks. The first one today in the morning, the second one this afternoon, and the third one tomorrow. And the plan is that I just give a short review on the theory of monetary risk measures today in the morning. So this is an interdisciplinary program, right? Many people from financial mathematics are of course familiar with this kind of theory, but for people from economics, this might be also something they have looked at, but maybe not following each of the details, and so that's the reason why I'm giving this talk in the morning. In the afternoon, I give another talk which is about systemic measures of risk. This is a talk which has very large overlap with the talk which I gave at the first conference here in August. So some people might have seen the talk already at the conference. So there's this overlap, but who has not seen it, for these people it might be new and interesting, and for the others maybe if there's some interest we can also more go into discussions. And at the first conference the talks were only 30 minutes, right, so quite quick, and in that sense we also have more time at the second talk. And the third talk, that's a talk basically about an integrated financial market model. If you've been at some of the conferences, you've seen a lot of network models. Of course, you've also read a lot of papers about it, or even have written papers about things like this, of course. And so what I'm going to do in the last talk is I present a new paper which I recently finished, which is looking at extensions of the famous Eisenberg-Noé model, and we integrate a lot of other effects like cross-holding, bankruptcy costs, and also fire sales. And so what we do is we provide an integrated model and also do a lot of numerical case studies trying to figure out how these different drivers of interaction basically trigger default cascades and systemic risk. But now let me just go into this talk. So this is about monetary risk measures. You all, of course, know monetary risk measures are basically functionals that are supposed to quantify the downside risk of financial positions. So if we look at portfolio optimization and risk management, then firms typically seek a balance between risk and return. And the regulator also would like to put certain constraints on the risk that certain banks can take. And there's one thing which one should emphasize right at the beginning. There is a conceptual difference between the concept of preference orders on the one hand and risk measures on the other hand. If you think of preference orders, this is of course somehow the typical concept in economics, which the choice of agents is modeled, right? But if you think about risk measures, there's a considerable difference. If you think of risk measures is basically a 0-1 thing. So in risk measures, you have acceptable positions and not acceptable positions. That's the key feature of risk measures. And from that, of course, you can also derive, if you want, a preference order, which is kind of induced by that. But the conceptual difference is that basically the main feature is that you have this 0-1 thing. You have the acceptable positions and the non-acceptable positions. And if you think about regulation, this kind of approach also makes sense. If you have a bank that optimizes a portfolio, of course, the bank, if you have a simple economic model, will optimize according to some preference order, right? So it has a utility or something like this, right? And it packs the portfolio accordingly. But the regulator, of course, usually cannot control the bank in each detail, and so the simple idea of a risk measure is basically to tell the bank what is kind of the set of options or the set of choices that is allowed, right, and the set of choices that is not allowed. And besides from that, the bank can do what it wants to. So that's a crucial conceptual difference between a risk measure and preference orders, despite the fact that, of course, also risk measures in the end induce certain preference orders. So here's the outline of the talk. So first I want to start with basic axioms and provide some examples. This is probably known to most here. And then there has also been an investigation of risk measures living on different domains. This has been a large industry in the literature to produce papers for risk measures on different constraints, but I just want to look at the univariate setting and explain that in that setting, and it actually turns out that in this setting it's also very useful for statistical applications, and you will later on see why. So that's part 3, and then in the last part I want to talk a little bit about certain recent developments in the theory of risk measures, which are very much related to statistical applications of these things. Okay, here is the axiomatic theory. So what should risk measures do? So they should have good economic properties, of course. If you think of a regulator, adequate assessment of diversification effects is important. Large losses should somehow be taken into consideration. And if you look at a time dynamic setting, of course, you want to also implement additional information and these sort of things. So you want to update the risk measures. So that's the first important part of properties. But of course, if you want to use these risk measures in practice, you also need tractable techniques for the statistical estimation of risk measures and efficient algorithms for the computation in realistic portfolio models. And there are some papers that also work on this part. The theory mainly focused on this part here in the beginning, but there have been quite a few publications in the last 5 years in this area here.
There's actually very little economics in the economic properties. It doesn't look at the incentives of the agents or what the risk measures are used for very carefully. It's some kind of an abstract.
Yeah, I mentioned that in the very beginning. So the basic idea of the risk measure, in my opinion, right, is that it is a little bit different from, let's say, preference orders, right? Usually if you model economic agents, they have preference orders, and then you model the choices they take according to those preference orders. If you are in a rational framework, of course, right? You could also have a boundedly rational framework. The idea of the risk measures conceptually, of course, we should later also discuss if this is a good idea and then also see how that can be used. But the idea of the risk measure is basically very simple, that the regulator constrains a bank by telling the bank what random outcomes the bank generates are acceptable in the end and which are not acceptable in the end. So it's not really a preference order, it's just giving a constraint on the bank in a very simple manner, but besides from that, leaving the bank do what it wants, right? So that's somehow the idea. So it's a very simple object. So it's kind of an object very comparable to a preference order, but it's in a sense an object with weaker.
You're talking about two different things, right?
Yes.
One is, people call this in the risk literature, they call this internal risk measure versus a regulatory risk measure.
Yes, yes.
And so if I want to optimize my portfolio, I will use my preferences over portfolios,
yes,
as usual. But if the regulator wants to put a limit on what I can do, they will put a 0-1 type of.
Exactly.
This is allowed, this is not allowed.
Exactly.
So both of them are called risk measures in the literature. And
yes.
And to be, same tools tend to be used, but actually it's two different objectives.
Absolutely, absolutely. Yeah, you are completely right. This is basically what I wanted to say, right? But these are the two sides one has to see. Okay, the axiomatic theory here, just to review that. So what's a risk measure? In a nutshell, it's just a functional row which maps from some random outcomes, random variables, for example, into the real numbers and assigns a number to it. So it's basically just a function assigning a number to the risk of the position. It's a way to measure risk. And the basic idea is that if you, for example, have your random variables and x is always less or equal than y for each omega, then what you want is that the risk of x is larger or equal than the risk of y. The second thing is the so-called cache invariance. And the cash invariance just formalizes that risk is measured on a monetary scale. You can generalize that, of course, right? So you can have multiple eligible assets, and there's literature about it. I don't want to go into that right now. So you can make that more general, but the basic idea is you want to measure risk in terms of capital. So what it actually means is if you have a position X and that position X has a risk rho of X, and now you add M euros or M pounds to this position, then the risk is exactly reduced by this monetary amount. This is somehow the idea. So that's the scale on which you measure the risk. And now comes basically also what Rama emphasized. A position is called acceptable if it doesn't have positive risk. And you can, of course, look at the collection. So it's usually a collection of random variables, stochastic process or something like this. In this setting, random variables typically. The set of random variables that has non-positive risk is called the acceptance set. And from this acceptance set, you can recover the risk measure as a capital requirement. So you can recover it as minimal amount of cash you have to add to the position such that X plus the cash you added is acceptable, right? So this is a way to recover the risk measure.
So here, you can define this measure on payoffs. There's no need to have probability.
That's completely right. You don't have to use probability if you want to. So you can also define that on payoffs. So
No, I mean, you can use probability, but the domain is a set of payoffs. And the way you compute your risk, you can use probability. So the probability is in the row, there's not in the domain.
it depends. It depends. You can do it either way. You can, of course, you're completely right. You can take this X as, let's say, bounded measurable functions without having any probability. And then you can come up with this here. And then, of course, you can prove the robust representation theorems that involve, again, probabilities or at least finitely additive measures. And then you have different scenarios and take a worst case approach. You're completely right. But what you can also do is, if you want to put a little bit more structure, of course, it's debatable whether or not you want to do that, right? Today we do that. You can also, of course, take here really random variables if you want, where probability measure is given. That's a different situation then. We will do that today because we want to also look at statistical properties, right? And there it's useful if you can basically talk about certain measures that generate your random variable outcomes, right? Or the probability of outcomes, right?
I still think this is a very limited view
Yeah.
of what regulators are doing. I mean, in practice, there's a lot of information asymmetry. There's a lot of, why doesn't the risk measure depend on the opacity of the assets? Why doesn't the risk measure depend on the level, I guess in that almost the same thing, level of information asymmetry or the complexity of the contract or the degree of ambiguity in the contract. I mean, this is like, we're engineers. We can go and measure things. We're going to go measure everything. We know the objective probability distributions. We're going to write them down. We've never seen anything in these tails, but we know exactly what their distribution is. We're going to calculate a risk measure as a function of that distribution. I think, and one of the reasons we get to this point is because these axioms are not looking at the economic situation we're in. They're just abstract axioms saying, suppose we know the joint distribution of all these random variables, and we want to measure something called downside risk. How would we do it? But it's not in the context of the economic problem, which is how are the players going to react to your risk measures?
You are completely right that this is not considered here, and I completely also agree with you that the question you raised are key, right, and extremely important. However, I still think that this might be valuable to some extent. It's a little bit like doing theory about preference orders, right? These are not preference orders. We had that point, of course, when we discussed it. But if you look at the theory of decision making and things like this, of course, you can first, at the very beginning, talk about preference orders and then ask whether or not they have a numerical representation and then ask whether or not they, how it looks like. And at that stage, where you just talk about these simple functionals, you also do not already have kind of really interacting agents that do a lot of stuff at this stage. But then, of course, afterwards, you use these concepts to formalize preference orders in order to understand economic systems. And this is more the view I take towards these risk measures, right? So it's a very primitive methodology to compute certain functionals of risky positions X. So that could be measurable functions, could be random variables. You can also talk about distributions whose risk you measure, and then you come up with this methodology. And so I completely agree with you that there's a lot of stuff that needs to be done afterwards. And of course, one needs to ask the question whether the way these objects are used in regular practice is kind of appropriate or non-appropriate, right? But this is just today. So your questions are absolutely valid, no question about it. But this is just today to review the stuff, right?
That's not what you're doing today.
Yeah, today it's just reviewing it, right?
I think here the related question is this trying to describe, this is a normative theory, is it trying to describe what people should do when they measure risk or optimize portfolios, or is it describing what regulators do, what risk managers do? And I think it started off as the second. So the paper of Artster and the co-authors, they looked at what was done in some exchanges and some banks, and they tried to formalize that. They didn't say this is what you should do. They said, well, if this is really what you want to do, well, here's the underlying theory.
Yeah.
It's not. They did. I think that's how it started. So, and then afterwards in the literature, people started using it as a normative theory, saying, well, here, let's optimize things with that, and that's where you run into Phil's question, because
Absolutely.
well, people are doing that, but should we actually do that? Is it the right way to do, or maybe we should do something different?
Yes, it's of course a very complex question that needs to be debated.
But-
No question about
But
it.
if you compare this, for example, with the theory of preferences and utility theory, well, the axioms are pretty similar to utility theory, except for the cache invariance, which basically normalizes one choice of increasing change of variance. But
Like assuming quasi-linear utility.
yeah, but the difference is that, if, for example, in von Neumann-Morgenstern theory, you don't assume you know the probabilities. So you say, you make choices under uncertainty, and it's as if you were optimizing an expected utility for some probability. But you're not assuming that people actually know the probabilities from the start. It's as if they are optimizing some expected utility. So it's a representation result. So
Yeah,
this is the big difference here. So if you develop it with knowing the probabilities, that's a huge assumption, and that's why, I mean, we know all this uncertainty literature, ambiguity literature, and of course it's very relevant. And actually, decision theory doesn't assume that in the axiomatic approach. Yes,
Savage axioms.
yes, savage axiom. Savage
You do-
axiom says
says-
you
say-
optimize as if you were doing expected utility maximization, but he never says, I assume you know the probabilities. It's not.
Yeah, I agree, of course, with this point, but it really depends on the specific way how you set up the risk measure. So you can set it up in different ways. You can set it up in the way you do it in some examples, right, where you say you don't have a probability, but you can also have examples where you have a probability, actually, and there is this area of distribution-based risk measures, right? That are the risk measures that are used in practice, like the value at risk, and that are risk measures that depend on the probability. And so, of course, once you have these things that are used in practice, value at risk, average value at risk, basically everything that's used in practice depends on the probability, then of course later on you can also ask questions about statistics. And that's something I also want to present today. So for that reason, we will today also look at the case where this really depends on the probability. Whether or not this is a good thing is a different question, and the disadvantage was already described by you, right? This problem that you have ambiguity, yeah? You have 19 uncertainty and these kind of things, right? And once you put a probability, of course, you basically say you forget about 19 uncertainty, right? And this is maybe not a good thing. But let's nevertheless just go through this just to see what's known and then see how we can maybe improve on that, or maybe which parts do not make too much sense. So one axiom here that's usually imposed is the semi-convexity of the risk measure. So the semi-convexity of the risk measure just means if you have two positions x and y, and you take a diversified position by taking a fraction alpha of x and adding 1 minus alpha of y, then this risk number, this risk measurement number should be, with this risk functional, be less or equal than the maximum of each of the risks, right? This is basically one key assumption which is usually made. And this implies the convexity of the risk measure. So this is a semi-convexity, this is a convexity. So there's sometimes also other axioms imposed. Classically, also the positive homogeneity is imposed. That means that if you scale a position x by some number, lambda, then the risk is scaled by exactly the same number. This is axiom or hypothesis that has been debated, of course, in the literature. So one can characterize these properties here also by looking at geometric properties of the acceptance set. So the risk measure is convex if and only if the acceptance set is convex. It is positively homogeneous if and only if A is a curve, right? So there are very simple properties. And so now comes the point Rama also mentioned very critically. Today I basically want to look most of the time at distribution-based risk measures. So if L here denotes a law of a random variable, right? So law is now something you can compute because you have a probability in the background, right? This is a situation now. Then risk measure is called distribution-based if the risk of X is equal to the risk of Y if the laws are equal, right? So this is the situation. And this is a situation which is, of course, the case if you have value at risk, average value at risk, utility-based shortfall risk, optimized certainty, equivalence, all these risk measures that are usually used in practice. They all have this property. So if you have now risk measures which are distribution-based, then of course you can also define a functional, which is a risk measure on the level of distributions. So instead of plugging the random variable into the risk measure, you can also plug its distribution into this functional, and it's defined like this, where L of x is the distribution of x, and that's a mu. So this is a definition which you can do if the stuff is distribution-based, right? So RO is just on the level of distributions there. So let's look at the examples. The first example everybody knows is value at risk. So that's the smallest monetary amount that you have to add to a position such that the probability of a loss becomes less or equal than lambda. So that's value at risk, right? The standard risk measure used something like 20 years ago. So that does not account for the size of extremely large losses and does not encourage diversification. And now let's here make a normative statement or quote a normative statement. So David Einhorn, who founded Greenlight Capital, a prominent hedge fund, wrote not long ago that value at risk was relatively useless as a risk management tool and potentially catastrophic when its use creates a false sense of securities among senior manager and watchdogs. This is like an airbag that works all the time except if you have a car accident, right? So that's what this guy said. Another risk measure, which is the basis for now Basel III and also the Swiss solvency test, is the AVAR. And the AVAR is just an average over the value at risk from the level lambda to the level 0. And this is a very popular risk measure, which is also discussed quite intensively by practitioners. That's coherent. So coherent means it's convex and positively homogeneous, is sensitive to large losses. It's the basis of the Swiss solvency test, a common alternative to the value at risk. In practice, it's distribution-based and continues from above. And also in the theory, it's interesting that's a building block of a large number of risk measures. So there's this theorem of Kusuoka, which is Kusuoka's representation theorem. He proved it in the coherent case, but then it was generalized in this diploma thesis here to the convex case. And that says that if you have a convex risk measure rho from L infinity to R, right? L infinity, if you deal with L infinity, then you're still in Rama's case because the P basically just gives you the null sets, right? So you are happy there, right? And so this is exactly the case Rama mentioned. L infinity is a space of random variables where the P only basically fixes the null sets, and so a Knightian uncertainty is no problem for the setting. But the problem starts, of course, if I talk about distribution-based risk measures, right? Then, of course, the probability measure matters. And so here it matters. So if we have rho that's distribution-based and continues from above, then one can write it down in this form. So it's a robust mixture of A-bars at different levels penalized by some penalty function. So this is a theorem of Kusuoka, which was generalized by Kunze, Fritelli, and Rosaccia Janine. And this is just something which is sometimes useful because this representation can be exploited mathematically, but it's of course also an insight that tells you that the A-var is a building block of this kind of objects.
But you can write that in terms of var too.
Yes, that's possible. No problem. Yeah, that's right.
A different integral.
Yeah, that's right. You can also do it with var. That's also possible. There are other equivalent representations, right? You can also deal with distortions and write that down with distortions and stuff like that, right?
So basically, any convex risk measure is a penalized the weighted sum of vars. That's what it says.
Yes, that's right. That's right. Yeah. So here's another one that is utility-based shortfall risk. So utility-based shortfall risk is a risk measure that basically makes this 0-1 decision. What is acceptable, what is not acceptable on the basis of a von Neumann-Morgenstern utility function, right? So that's basically what it does, right? So you have a convex loss function here, that's L, convex loss function, interior point of the range of L, and then you define acceptability just by saying the expectation under P of L of minus x is less or equal than that. And of course, you can also rephrase this with a utility, right? If you take u of x, little u of x as minus L of minus x, right? Then you are back in the von Neumann-Morgenstern surface representation theorem, right? And then you can just say, okay, everything is acceptable which has a certain minimal utility level, or which has a certainty equivalent that is above a certain number which you impose at the minimal number you want to have. So that's also possible to do that in this equivalent form, and that induces also a convex risk measure, which is called utility-based shortfall risk, and that can easily be computed numerically. So there are good algorithms to compute that. That's no problem, because it's a solution to a stochastic root finding problem, right? So that's what it is. That's this equation here at the bottom. So it's convex, it's sensitive to large losses, it's distribution-based and continues from above, easy to estimate and implement. So here's another risk measure that's called the divergence risk measure. So that's basically defined in terms of G divergence. So you have a function G, which is lower semi-continuous and convex with superlinear growth. And what you can do is you can generalize the concept of relative entropy, right? So instead of using x log x, right, in order to define the relative entropy, you can also take such function G and define a G divergence, which generalizes that. And here, this is basically what Rama said, right? This is a robust representation, right? A robust representation, where here the robust representation is now penalized in terms of a G divergence, right? This is basically what it is. And these divergence risk measures, they are, one can show that they're distribution-based, right? So they're distribution-based. And they are actually the same as the class of so-called optimized certainty equivalents, right? Which can be shown here. And that is a concept which was introduced by Benthal and Tebuli. So that as a class of risk measures, right, that generalizes in some way also the AVAR. AVAR is a special case of these risk measures. And these risk measures here, they can be computed also from this equation here. They can also numerically be implemented very nicely because they correspond to a stochastic optimization problem where you have to optimize over one parameter. So that's very related to utility-based shortfall risk, where you have to solve a stochastic root finding problem, right? And here you have to solve a stochastic optimization problem in one parameter. And that can somehow be reduced to the same techniques you can use for utility-based shortfall risk, because you look here at the first order condition, right? That gives you a stochastic root finding problem. Then you find the maximizer of this equation here, plug that in, and then you just have to run a Monte Carlo simulation to compute the risk measure. So instead of utility-based shortfall risk, where you just have a stochastic root finding problem, here you basically have a two-step situation. Yeah, a special case of that is the entropic risk measure, which is a risk measure which you get if you take relative entropy, and average value at risk is also a special case of the divergence risk measures. Yeah, looking at the time, maybe I skip over the next example and go to domains and dual representations. So this is also very much related to what Rama said. So if you have L infinity and you have a risk measure on L infinity, this risk measure does not need to be distribution based, right? So you can include 19 uncertainty, right? Then one can show that the risk measure can be represented in this form here. And this is also what Rama said. The risk measure itself is not necessarily distribution based. However, of course, it has to respect the null sets of P. So if two positions only deviate on a null set, the risk must be the same, right? That's what the P fixes, the null sets, right? And if you have such a risk measure, then probability, as Rama already said, enters here in this representation. So you can compute any such risk measure under weak conditions here, weak technical conditions, as a supremum over a set of scenarios, and the scenarios you have are all the probability measures which are absolutely continuous with respect to P, right? Which respect, that's what it is, they respect the null sets of P, right? That's what it is. And then you evaluate the loss of the position X by just taking an expectation with respect to this probability measure. And the expectation is penalized by some number which depends on this scenario, right? The probability measure you take to compute the expectation. And any risk measure can be basically obtained as the worst case, right, of these expectations that are computed in this fashion here, which are penalized according to the alpha. So this is this general representation theorem of risk measures. However, if you go to the space LP, right, then of course, what's in the space LP now depends on the probability measure, right? The space L infinity is, of course, invariant under equivalent changes of measure, right? Because it just depends on the null sets, right? It doesn't depend on the probabilities that are actually imposed. But LP, of course, doesn't have this property. If the P is between 1 and infinity, in this case, the space itself depends on the probability measure, of course, right? You need to check intrusibility and stuff like this. It depends on how much weight you add to certain sets in your sigma algebra. In this case, you get a robot representation theorem, and here the advantage is that you don't...
The previous case...
Only through the null sets. Only through the null sets.
Yeah, but that's...
Yeah, but that's a big difference.
But for
right?
example, look at all the issues we had with the rating agencies.
Yeah.
The issue was the rating agencies use the model.
Yes.
Obviously, they didn't use exactly the same parameters,
Mhm.
each of them, but the basic problem was that in their model, there was no scenario where housing in the US
Yes. Yes.
decreased in
You're
value.
of course right. Yeah.
So that's a
Yeah, yeah,
offset.
yeah. No
That's
question
a
about it.
concrete example of offset.
You are completely
So
right.
now you can
Yeah.
change the parameters, you can change the drift or whatever,
Yeah.
but as long as there's
Yeah,
no
yeah.
scenario where the
Yeah,
housing
yeah.
prices go down, you're never gonna fix that. So, I'm not sure whether you should call this a robust representation.
Yeah,
I'm a
but
little-
let's maybe just
But I think there are robust versions of
say
this.
that you are. I mean, your point is absolutely true. There are just different levels of imposing assumptions, right? So in the LP case, right, the probabilities you assign to certain sets, they make a difference, right? In the L infinity case, it is just the null sets. But of course, as you said, it's completely right. Also imposing what is a null set and what is not a null set, of course, is an important modeling assumption, since, as you just described, it can definitely happen that you assign a probability 0 to something which is absolutely relevant. And of course, the model itself is not innocent just due to the fact that the actual probabilities which you use don't matter, right? So it's completely right what you said, yeah, of course.
Is this supremum why you don't need charges here?
Hmm?
I mean, the dual has charges in it. Does the supremum why you don't need to include charges?
Yes, you can also look at the coherent case, so if you have the positive homogeneity, then what you do is you take a supremum over a subset of these probability measures, and then the alpha here vanishes. So in other words, the alpha can just take the value 0 and the value infinity, right? So those where it has the value infinity, those do not need to be considered in the supremum. That's completely correct. That's a coherent case. So in LP, we have the problem that also somehow the probability level matters. And here you don't have to impose any assumptions, additional assumptions, like this weak lower semi-continuity, because here you have nice dual spaces, and you also have the theorem of Banach-Alaoglu and these kind of things, right? So everything works out, and here you have a maximum, right? So this is just different representation, where of course here now the representing measures, they need to have densities with respect to P, which are in LQ, right? Which is a dual space of the LP. So this is just the way it works in this case, right? So it's easier, right?
So all these theorems look like they're just representations in terms of the support function.
Yes,
the convex.
absolutely. Yeah, you're completely right. You have a convex set, and then you just have affine functions, right? And you just go around it. Completely right. That's what it is. So it's a classical Fenton-Moreau theorem, just applied to these particular spaces under some additional structural assumptions, which allow you, once you have this dual representation, to select a subset of the dual space in order to do the representation, right? Usually you have to take the whole dual space, but because of these assumptions you make on the risk measure, you can restrict to probability measures, right? So that's basically what it is.
That's why you don't need the charges.
In the coherent case, you don't need such charges. In the convex case, you need it, but still you can just focus on probability measures when you take the supremum. Yeah, usually you have to take here the dual space, right? So here you would have to take, here we would have to take not only probability measures, we would have to take basically all signed measures which have densities that are in LQ, right? And so this is a little bit more special in this case. Okay, so time is running, but this is something I need to mention in order to make what I want to do later understandable. You can generalize this LP stuff to so-called ordered spaces. And what you just do is in ordered spaces, you replace this x to the p function, which you have in the LP case, right? You replace it by more general functions. So you just take convex functions, basically. They are called Young functions. And what you can do is then you can define an ordered space. An ordered space is just this space here which has the property that you look at all random variables that have the property that these expectations here are finite. So you look at psi of some constant times the absolute value of x, and if that's finite for some c, you say that the x belongs to the ordered space. And the ordered space is actually a normed space. It's even a complete normed space. It's a Banach space if you endow it with this norm here, which is a Luxembourg norm. And in the LP case, this is just the same as the LP norm, right? So
I thought ordered spaces, the C function was a function of the state.
The C function is a function from the positive real line to the positive real line.
I thought
And so what
Merchanway
you
could
do
also
is-
depend on the state.
This is deterministic, the psi. So it's like the x to the p's power
Yeah,
in the LP case.
that's
So
right.
it's just a deterministic function. And this deterministic function is just used to check this integrability here and to define a corresponding norm. And you'll later see why this is important. You can also define an ordered chart, and the ordered chart, the difference of the ordered chart to the ordered space is that here you check that this integrability condition holds for all the C, right? In the ordered space, just it needs to be checked for one C. That makes a difference. So that's a linear subspace of the ordered space, and if psi is not infinity, if it's always real valued, then you can actually show that this inclusion holds. So L infinity is included in the ordered heart, the ordered heart is included in the ordered space, and the ordered space is a subspace of L1. And the ordered heart is a closure of L infinity in the ordered space according to the Luxembourg norm, right? This is what it is. So the important thing is now what comes now. The important thing is if a certain condition on the way of this psi function is imposed, right? The growth of the psi function basically says it just is allowed to grow like a polynomial function. That's basically what it says. Then one has that the ordered space is equal to the ordered heart, right? The spaces are equal, and this is in particular satisfied for LP spaces, right? So in the case of LP spaces, the LP space is equal to the ordered heart, corresponding to this psi function x to the p, and it's equal to the ordered space. The whole thing is not the case if you, for example, consider exponential Young functions, like e to the x minus 1. That does not satisfy the delta 2 condition, and the ordered heart and the ordered space are not identical. Why I'm mentioning this? The reason is the following. This space here is the space which you need if you want to define the domain of the entropic risk measure, right? The entropic risk measure. The entropic risk measure has been used in many papers in math finance, right? But as you see here, these nice conditions here, up here, they are not so satisfied for the entropic risk measure. And later on, we will see that the robustness of risk measure depends on this property here. And you can only obtain robustness, if this property here holds. If it doesn't hold, you basically have risk measures which are completely non-robust. And in particular, the entropic risk measure is a completely non-robust risk measure. And despite the fact that many people use it, right, for nice mathematics, because it's so simple, from a practical point of view, it's completely useless, entropic risk measures. The other risk measure is something we debate later, right? Rama has a paper on that, and this theory can be used to look at this aspect in more details. Okay, on all its hearts, you also have a robust representation which looks very similar like this representation you have in all P spaces. I don't want to go into the details, that's not so important. The following is more important. This is somehow the key thing we need later, right? The key thing is, if you have a risk measure, which is distribution based on convex, and it is defined on L infinity, then it was shown by Filipovic and Swindland that this risk measures always admits a unique extension to L1, which is convex, monotone, cache additive, and lower semi-continuous with respect to the L1 norm. So what does the theorem say? The theorem says if you have risk measures on L infinity and you have risk measures on L1, right, which may take the value infinity, then they equivalently define a risk measure. So it means if you want to define a risk measure, define it on L infinity or define it on L1 or define it wherever you want to. As long as you define it on L infinity, you define it. Full stop, right? Nothing to be said about it anymore. You just have to define it on L infinity. So that's what it says. So that's nice. But now comes the second thing, which is nice. This is this result. And this result says that the finiteness of the risk measure on an all its heart, which is always a subset of L1, that this determines the continuity properties of the risk measure. Right? That's the second key result here. So if rho bar, which is this extension here, is finite on some all its heart with finite Young function, then it is continuous on this all its heart with respect to the corresponding Luxembourg normal. And that is actually key also later on to understand robustness of risk measures, right? Which can be analyzed in a more sophisticated way. But before we go to the robustness, I want to talk a little bit about convex level sets and elicitability. So recently there has been a lot of discussion about backtesting risk measures and predicting risk measures and things like this. And Gneiting, he wrote a couple of papers which were kind of well received by a large number of people, and so whether or not these papers go into the right direction or not is a different question, right? But at least it was debated. And some people, of course, also discuss these things, and they ask themselves which are the elicitable risk measure. I'll come to a definition later. But I can already mention it at this point. If you look at the theory of robust statistics, then you probably know the concept of an M estimator, right? So that's a generalization of a maximum likelihood estimator. And this is a particular statistical functional of distributions, right? That's an M estimator, was invented by Huber in 1964. And an M estimator is basically the same as an elicitable statistical function. It's basically the same, just different name, right? And if you have things like M estimators, you can also employ them in generalized regression, right? Regression is you have some kind of a score function like x squared, right? And now you put your line according to this penalty, right? Your error function which you have. Instead of x squared, you can take other error functions, right? And then you get, of course, a different line, right? And so statistical functionals, which are minimizers to these penalization error functions, they are elicitable, so that are the M estimators. The formal definition is on the next slide. And now, of course, you can ask the question, which risk measures are elicitable? And we will give an answer to that. So this is a generalization of basically the stuff I mentioned. This is what the M estimators are, and this is also what you do in the regression with a special scoring function. So the scoring function is basically the error function. It's a function from r squared to 0 infinity. It has the properties that is always bigger or equal than 0. That is 0 if x is equal to y. So think of s, for example, as x minus y squared, right? So that's a typical example. It's increasing in x if you move away from the y, right? So that's what this says. And it is continuous, it's just a regularity property. And now a statistical function is called elicitable on M if there exists a scoring function such that statistical functional is recovered from this integral here by minimizing this functional here. This is what an elicitable functional is. So that's basically an M estimator in statistics, right? And you can think about that just looking at S of x and y being the special case of, right, absolute value of x minus y squared. So this is kind of the standard case of regression. Okay, so it's obvious from the definition that if you have such a functional that it possesses convex level sets on the level of distributions. This is a result of Osband from his PhD thesis in 1985. So it says T of mu is equal to T of nu. That implies that also T of the mixture of these measures, mu and nu, has the same value, right? So that are the convex level sets. And this result is key to the recent characterization of all elicitable risk measures, which can actually be based on that paper that has a representation result for these risk measures in it, but it has been applied to elicitable risk measures in this recent paper here. So for this we need some topological preliminaries. So if you have spaces of measures, then a typical topology you use is a weak topology on it, right? This is generated by the continuous bounded functions on the space of measures. But instead of that, you can of course also try to capture the deviations in the tails, which is not done by the weak topology. And the generalization that's usually used in this respect is a psi-weak topology, where you look at measures which integrate a continuous function, so it is, for example, increasing to infinity, and then on Z space, you can introduce a psi-weak topology by defining the initial topology, which maps mu into the integral of f y mu dx, and the f comes from the space psi psi, and that is the space of all continuous functions f, such that f is less or equal than c times psi, right? It's just a generalization of the weak topology where you now consider the tails, right? You measure also deviations in the tails, that's what you do, right? And so the weak topology is insensitive to the sales for unbounded psi, and the phi weak topology is finite, does not neglect deviations in the measures of the tails. And so now if you have a distribution-based risk measure, then of course, as we did in the beginning, you can also interpret this distribution-based risk measure as a functional on the level of probability distributions, and you can define an acceptance set on the level of distributions instead of on the level of measurable functions, right? So that's what's done here. So that's the acceptance set on the level of distributions, and here on the level of the rejection set on the level of distributions. And as I mentioned before, if you have an elicitable functional, then the level sets on the level of measures, they are convex. That means in particular, that's the acceptance set and the rejection set are convex as sets of measures. That means if you take two measures and take a mixture, right? The mixture is again in the set. Okay, so here's this old theorem from 2006 in mathematical finance. If you have a distribution-based risk measure, then the following things are equivalent. The acceptance set is psi weakly closed for some gauge function psi, and the acceptance and rejection sets on the level of random of the level of probability measures are convex, right?
How can they be both convex?
Yeah, you'll see what the answer is, right? I have it. I mean, here's the answer basically. They are both convex, if and only if they're both convex. I mean, first of all, if you have an elicitable functional, this is satisfied, right? Elicitable risk measure implies convex level sets. Convex level sets implies
They
that
form
both
a
acceptance and
partition
rejection.
they form a partition.
Yes, yes. They partition the measures in such a way that mixtures of acceptable distributions are again acceptable, and mixtures of rejected distributions are again rejected. That's
Just a
what it says.
geometric question.
Mhm.
It's hard to.
It's a linear feature, right? It's in a fine kind of object, right?
But it's not defined. The set of
Yeah, I mean, you are right.
probability measures is a
Quotes
convex
and
set.
quotes, right? I mean, it is just what I said, right? In this case, it means if you take two acceptable things, right? Two acceptable distributions
Yes.
and the mixture, then it's again acceptable. And if you take,
Why?
that's a hypothesis.
But
And this hypothesis is necessary for being elicitable.
But where does this come from?
I mean, elicitable is
I
the thing of the
understand
M
that if you
estimators.
take two random variables, I understand that you take complex combination, it's a portfolio.
Yes.
If you accept each of the two investments, you should accept the
Right.
portfolio. But the
You are asking
mixture-
for an economic interpretation.
Well, yeah, what does that correspond to? Like, I take two distributions.
Yes.
What does the mixture correspond to in terms of?
Yeah, as a mixture is basically a two-step random mechanism.
Yeah, I understand.
You right?
Throw a coin
And then you choose one, and then you have randomness according to one of the things.
Yeah, but why do you impose it at the same time on the non-acceptance set and the acceptance set?
Well, I do that because
Because
of
for
this result
acceptance,
of
maybe
spend.
I understand. You say if you accept this risk and you accept this other risk,
Yeah.
then if you have a lot,
Yeah.
but you think of a lottery where you can get
Exactly.
with probability alpha one and I won myself with the other, you should accept that.
Yeah.
Lottery. Okay, fine. But for the non-acceptance, it's kind of the opposite. So why should you?
But
have
this is, you're mixing in probabilities. This is one of the axioms in, when we derive on Morgan's.
for acceptance, but for
No, it's not for,
non-acceptance.
in mixing in probabilities, it's saying if you're indifferent between A and B,
Yeah.
you're indifferent between any mixture of A and B.
Yeah, but
So you can, so
for non-acceptance,
for both. It's in probabilities, it's not in quantities.
yeah, I understand.
So if you're indifferent between A and B, then you're indifferent between a 50-50 chance and B. It says you don't care about the process.
Yeah.
We have this, there's this example which says,
Yeah,
you know,
this is indifference.
which of your children get a cookie and you flip a coin and should you be indifferent between giving the first one the cookie or the second one cookie or doing a 50-50 flip?
Yeah, that's for
And
indifference.
there maybe you're not indifferent because of the process, but usually we assume that if you're indifferent between this and this, you're indifferent between any lottery involving them. That's usually one of the axioms.
But maybe
Morgan Stern utility.
Yeah, for indifference, I understand. For the acceptance sets, I understand.
If
but
you have it for indifference, and then you have it for the acceptance and rejection too. Given
Maybe,
just a little structure.
just to get to the result, maybe it's good to move on. But before we
no,
do
the
that,
only thing it has nothing to do with risk. It's just a geometric question. What kind of set can be partitioned into two convex sets?
the answer is on the slide, right?
Separating hyperplanes.
I have the answer on the slide because it's a characterization theorem,
Okay,
right?
so
The,
linear.
I mean, but before we let me maybe I mean the question is of course valid, no question about it. The question is how to understand these things from an economic and mathematical perspective. But first, let me make again the storyline clear that we are talking about here, right? Of course, there are other questions related to it, but the storyline was just the following. You have M estimators, also called elicitable functionals, right? You have risk measures. And now the question just is, if a risk measure is elicitable, so if a risk measure is an M estimator, right? What are the risk measures that have exactly this property? So, Osborne showed that if you have something elicitable, then the level sets on the level of distributions are convex. If you have a risk measure that's elicitable, then the consequence is that, of course, its level sets on the level of distributions are convex, and as a consequence, also the acceptance set is convex and the rejection set is convex. And now I'm just asking the question, which risk measures have this property, right? Of course, there's the economic question and also the mathematical question, what does this convexity mean? No question about it. But that is the storyline that we have here. When I wrote this paper originally here, do we have the result? Here's the result. When I wrote this paper originally here, I had a different motivation because I didn't look at elicitability or something like this that became popular in 2011. This paper is from 2006, right? So the other question was different. The question was, if you take a risk measure and you measure risk dynamically in each point in time, but you just have a terminal position, right? And now you update your information from time to time, right? And now you know the following. And how do you evaluate your risk? The simple idea was just you use the risk, evaluate it as a conditional distribution, right? And the question was now the following. If you know for a position that tomorrow I will accept it no matter what, right? then a weak consistency property in time would be that I say when I know that tomorrow, no matter what, I accept it, then I should already accept it today. The second property was, if I know for sure today that tomorrow I'll reject it, then I reject it today for sure. That's a weak time consistency property, is weaker than the Spellman principle, which is usually considered in time consistency of risk measures. A weaker property, weaker time consistency property. And if you do that, then you can show that if you just take a single risk measure doing this whole procedure, this risk measure must have this property, because you can translate just by doing some Bayesian computations, basically, right? That translates into convexity of sets, so mixtures, right? And so that was the motivation originally for this hypothesis, right? And then, of course, one can try to solve the problem, right? And to characterize it, and this is what comes out of it. So what comes out of it, a risk measure has these two properties here, if and only if the acceptance set has this structure, right? So it essentially means that the class of risk measures with this property is exactly the class of utility-based shortfall risk measures. Right? This is what the theorem says. Right? And it's a little bit more general because we don't require here that the risk measure itself is convex according to the original notion of convexity. Right? So this L here doesn't have to be convex. It can also have jumps. So the value at risk is included in this characterization theorem. The value at risk is included, right? Yeah. So it's more general. But if you have convexity, right? If you have convexity and the assumptions of the preceding theorem are satisfied, then rho is convex if and only if the loss function L is convex, and rho is coherent if and only if it is a so-called expectile, right? In the paper from 2006, this corollary was also mentioned, and also these risk measures, the expectiles, were written down there, just not naming them expectiles, because I hadn't seen anything of this elicitability risk measure
So
literature.
this is the difference between utility and the risk measure, because you can have, basically with the risk measure,
Yeah.
the linear indifference curve at the critical level you're important to says that you can use a linear utility function. But you can have all the utility functions linear and not parallel, like in beta utility. And then you can't use this. So this is the difference between a risk measure and the...
Yeah, but this property here is different from the Kersh invariance, right? This is a second property. So here you have a convexity of on two sides. So in a sense, you have a certain linearity of the boundary of these objects. But this is different from the Kersh invariance, which is the fact that the utility increases exactly by a number if you subtract a number from the position. So there are two different things, right? So this is a very special case of a risk measure, which is the case of these convex acceptance and rejection sets on the level of risk measures. Let me just mention, I think I also ran out of time, so I should probably stop in a couple of minutes. Let me just mention that the result has been generalized by Delban, Bellini, Bignozzi, and Siegel recently in the case of convex risk measures, right? There's no paper out there yet, but according to personal communication with them, I know that they've done this, and they also showed me what they've done. So I firmly believe them that this is correct, right? So what do? They don't need this topological property. Yes, they don't need this topological property.
Can you show the next slide?
Okay. They don't need the topological property in the convex case, because in the convex case, you can show the characterization result.
So what is the statement? What's the result? Elicitable risk measures are which one?
Okay, that's on the next slide. So if you have elicitable risk measures, then they are convex risk measures if and only if they are utility-based shortfall risk loss function L. So the convex elicitable risk measures are exactly the utility-based shortfall risk measures. That's a statement, that's a consequence, right? Yeah. And the coherent are the expectiles, right? And the coherent and co-monotone is just negative expectation, right? And AVAR is not elicitable, that was already shown in this old paper, right? Because its acceptance set is not convex on the level of distribution, but it was independently, again, shown igniting in this other language.
VAR is elicitable.
Well, it's also elicitable, and it's also obvious from the theorem, because here, if you take an L that jumps by 1 at 0, then you have here var, which is included in the characterization theorem.
Yeah, but for VAR, these things are not convex. So.
They're convex. This is on the level of distributions.
Oh, the level
Yeah.
of
So this theorem also applies to var, right? That's somehow the key difference between this theorem and the theorem by these guys. They assume that the risk measure itself is convex in the conventional case, and by this additional assumption, they can get rid of the topological assumptions that I make. Yeah, right. That's what they do. Okay, so I don't have any time anymore, but this is something I very quickly want to mention. Just to mention, my next talks are much shorter, right? So I have a lot of slides because of the review. In the next slide talks, I have just a few slides. So hopefully I don't go over time. But robustness, this is important. I mean, convex risk measures have been criticized because they are not Humpel robust. This is also something Rama pointed out, right? But Humpel robustness refers to the notion of weak convergence of probability measures. And weak convergence basically means that you don't look at the tails anyway. And so the question one can ask is, should we measure the downside risk of financial positions with tail insensitive but Humpel robust functionals? If something is Humpel robust, it's tail insensitive, so is it the right way to go? And as Rama and others pointed out, they are not Humpel robust, but what's the consequence of this statement? So that's the question. And that has recently been investigated very carefully in a series of papers by Kretschmer, Alexander Schied, and Seele.
Yeah, but I'm sorry, but we never talk about Humpel robustness.
Okay, maybe it's the other paper.
We
right?
talk about tail robustness. It's a different notion, and it's exactly the same as Kretschmer and etc.
Okay. So yeah.
It's just the same thing.
Okay.
But anyway.
I look at that again to quote it completely correctly. My statement was not completely precise, apparently. What they point out is that robustness just depends on the metric which you use to measure the distance, right, on the tails. And we don't have the time to go into this very carefully. Let me just mention that the robustness of a functional can be characterized as being equivalent to whether or not the extension of rho is finite on its space, right? Or the risk measure itself, considered as a function on the level of distributions, is continuous with respect to a corresponding psi weak topology, right? And if any of these conditions holds, then the risk measure is robust, right, in a generalized Humpel robustness set as outlined in these papers. I don't really have the time to explain this here very carefully. So let me let us just take this last part in a sense, for anybody who is interested in robustness of risk measures, as an advertisement for these three papers by the three guys. So one paper is mainly containing the main results, which are relevant for risk measures. It's a paper which appeared in January, I think, 2014 in Finance and Stochastics, right? So that's kind of the key paper, which summarizes the results for the risk measures. But of course, you can also write down this more generalized Humpel robustness theory on a more general level, and that has been done in the other papers. And so if you do that, what you can do is you can also define an index of qualitative robustness according to their theory. And what one gets out of it is that the index of qualitative robustness is just 1 over the smallest pay, such that rho bar, the extension of rho, to L1 is finite on an LP space. So that's basically what it is. And of course, the most robust thing you can get is if you can, for example, define something on, let's say, L0, right? But L1 is also okay, but if you take an LP space with a P which is larger than 1, you get less and less robust. And L infinity is, of course, the least robust case you can have if you can not extend something from L infinity to any larger space. And it turns out that the var has an index of qualitative robustness which is infinite, right? So infinite is the best. And all convex risk measures have an index of qualitative robustness that is at most 1, right? 1 is the maximum you can get. And 1 is exactly what you get if you can extend your risk measure finitely to L1, right? That's what you get. And so average value at risk has an index of qualitative robustness of 1, right? And if you look at utility-based shortfall risk, right, you can also look what the index of qualitative robustness is. So if you have expectiles, expectiles have also an index of qualitative robustness of 1. So it's exactly the same as the A-bar, right? And also the expectation, right? There's an index of qualitative robustness of 1, right? The expectation. And if you look at power loss functions here in utility-based shortfall risk, then of course the power you take determines the index of qualitative robustness. So if you, for example, take the square, right? The square, which corresponds to, let's say, the stuff you usually use. Also, when you do standard regression things, you want to have finite variances and x squared and things like this. So you get, in this case, when the p is 2, you get a half. Or if x is some x to the p, you have some other p, you get 1 over p. And the entropic risk measure itself, that's not finite on LP space, so you get the index of qualitative robustness 0, right? So that's completely non-robust, right? Okay, so maybe I put a lot of I put too many slides together, I guess. But anyway, let's just wrap up very quickly. I presented the axiomatic theory of risk measures. We already had some discussion about whether or not this is kind of a reasonable approach for practical problems we are faced with, but I think this is a debate we should continue, right? And we couldn't really resolve that already, but that's interesting. Then I talked a little bit about the domains of risk measures. Why did I do that? Because if we talk about the domains of risk measures, we can actually see that these domains of risk measures play a role in the continuity properties of the risk measures, which are again, as we've seen very quickly at the end, are equivalent to robustness properties of the risk measures in terms of generalized Humpel robustness, as recently introduced by these 3 guys. And then there was another question regarding statistics of risk measures. Recently there was this notion of elicitability debated quite intensively in the literature, which is basically almost equivalent to the concept of M estimators of Hubert from the 60s. And then you, of course, can ask the question, which risk measures are the elicitable risk measures? And as I pointed out, that's a question to which the answer is basically known for almost 10 years, despite the fact that that was overlooked in the literature until this year, right? But that's basically done to characterize that. Whether or not elicitability is a property that makes any sense for practical applications, there's of course also something you can debate, right? And there has been recently a paper by Mark Davis that's discussing that is very critical about the notion of elicitability. So that's also, of course, an ongoing question, whether or not this is useful, and if it is useful, in what sense it might be useful, right? Okay, good. Then, first of all, sorry for going over time, and I promise to you that the next talks will be much shorter and more condensed. But they are also talks that present a paper each, right? And do not really give an overview about a lot of material. So hopefully I managed that in 60 minutes. Thank you very much. Any more questions?
So the notion of psi robustness
Yeah.
in these papers,
Yeah.
we call them C robustness, but apart from C and psi,
Okay,
it's the same if you look in the paper.
Yeah, I look at that again. So you did actually the same stuff somehow,
No,
right?
but they just take psi of x equals x to the p, special example. We
They
say-
do it generally.
No,
right?
our notion of
Yeah.
robustness is
But you
simple.
took x to the
Robustness
power.
means
Yeah.
you take a risk measure.
Yeah.
And you say you have the wrong probability distribution. Now you want
Yes.
the risk measure to be robust to perturbations of the
Yes,
probability
yes,
distribution.
exactly.
So robustness in the classical sense looks at all perturbations in the space of probability measures.
Exactly.
You need continuity in the space of all probability measures because that's what robustness is.
Yes.
And we say, well, that's too vast because
Okay.
we're not interested in all probability measures because we have a model, we have an idea of where the probability measure lies.
Yep.
So we take a subset C, plausible measures.
Yep.
So this can be L1, this can be LP, but this can be Gaussian measures, this can be student elliptical distribution, whatever your model is. And then we look at perturbations in that class. So we say it's robust if inside that class, it's continuous to perturbations within that class. And it can be LP, but it doesn't have to be LP, it can be anything you like.
Yes.
We give examples where you change this class and you see whether inside your preferred class of models, it's robust to
I see.
perturbations. And of course, the bigger this class, the more stringent is the condition. But what we show is that if you take these popular coherent risk measures, they're not even robust to perturbations within their own domain.
Okay, but
Which is what they.
yeah, but
it
it
doesn't have to
depends.
be-
What
For
you're
example,
saying, yeah, I
it's
see the
even
point.
worse,
But
it's even worse.
your statement depends also. It does not only depend on the domain. It also depends on the distance measure you use on the domain, right? And so here, this is
No, it
somehow the
doesn't
key
depend.
feature.
It doesn't
It
depend.
depends on the distance measure. So here, what they do is, and actually it's equivalent if you change the distance measure accordingly.
No,
So
it doesn't depend because there are two notions of robustness. One is qualitative robustness,
yes,
which is exactly the same in their paper, in our paper, but the other one is
Uh-huh.
quantitative robustness, which is you do perturbations, you compute a directional derivative. You say, if I do perturbations in this direction inside some class, what's the impact on the sensitivity analysis? And we do both, and we show that
Okay.
these examples of coherent risk measures are neither qualitatively robust in this, even if you take a very small class, like only elliptic distribution, which is kind of a minimum thing, nor quantitatively robust in the sense that the sensitivities blow up.
okay. I have to
That
look
one
at
is
your
not-
paper again,
Yeah.
but I think there's still a subtle difference, and this is this thing here, right? This little thing here. So what you do here, right, is, I mean, what you do here is, what do you do here? You generate samples from a distribution, right? Independently. That's what this means. So you have a product measure here. That's what you do here. And now you sample and sample and sample and sample again independently. And what you do now is exactly what you say. You sample from something which is a little wrong. That's a new. You sample from something which is a little wrong. And then you want to ask whether or not the risk you get, right, which is this, from the wrong distribution, has the estimator has a distribution which is close to the distribution of the estimator, which you get when you sample from the right thing. And the key thing is, of course, you have to say, in order to define robustness, not only in which set you choose this perturbation, but also according to which metric you pick the neighborhoods, right? And so that's also important to choose a distance measure here correctly. And the distance measure which needs to be chosen here in order to obtain the results is a distance measure which metrizes the psi-weak topology. So in their case, it's this psi-Prohoff metric. And so if you, I don't know exactly what you did, I have to look it up again, but if you change the
Yes, but
domain
they
alone,
don't-
but use
They don't use
this
the end.
distance.
They don't use the end. They use all the domain. They
Yes.
do not do what you say in the previous time. They use all the domain. Whereas the essential thing in our analysis is we restrict
Okay.
to a small set. And even if you show that even if you restrict perturbations to a small set,
Yeah.
it's not robust, that's pretty bad. So we show that even for elliptic distributions,
Mhm.
there's not a robustness of the coherent risk measures. So that's a very strong statement, because it means even if you use only
Okay.
Gaussian and student, you're not robust. And the psi here, there's no economic interpretation. I mean, why do I use this psi or that psi?
It's a measure of the distance in the tail.
Yeah,
right?
but
So you have to pick what do you want to use, right?
Yeah.
You know what's more difficult, what's easier, right? Okay, but very interesting. I'll look at that again and also compare this more carefully. Great, thank you very much. Thank you.